Hello, everyone, and thanks for joining the Lattice Developer Conference for 2024. We're going to talk today about the FPGAs or doing an introduction on FPGAs. So my name is Murad Zakama. I'm an application engineer with Lattice Semiconductor. I'm actually with Lattice Insights, the official platform, training platform for Lattice, developing new content and doing instructor-led training. My main area of expertise is software and hardware, the FPGA architecture, some of the design techniques, best practices, and timing constraints. As for the academic background, I have a double E with master degree in microelectronics and an MBA from University of Quebec in Canada. With that, let's go through the agenda. So in the agenda today, we have 5 or 4 main sections. So we're going to start by going through the advantage of an FPGA. Why should we use an FPGA? The second section will be the basic gates and logic elements, which are the building blocks for any logic system. And then we'll go to the FPGA architecture in more details and have an example Nexus family trying to go through the architecture and the building blocks of this architecture. And the fourth section is design techniques. So when you doing a design, you have some trade-offs, let's say for latency versus throughput. So we're gonna go through some design techniques to maximize one or the other and making sure you're making the right decisions. And the last section is about frequently asked questions. So why should you use an FPGA? So what's the advantage of FPGA implementation? So that's what you're gonna see in this section. So you may be familiar with some of the glue logic that you see on the left-hand side of the slide, where you have PWM, SPI chip, you may have 7400, 74 logic, you may have microcontroller, level shifter. All these are discrete components that could be easily integrated in the smallest device from Lattice. So the ICE40, for instance, the ICE40 Ultra Plus, which is the a 2.1 by 2.5 millimeter device, usually used for consumer type of application, but it can integrate all these components or multiple of these components in one device. And we're talking about 8K lookup table. So we're going to see what is lookup table later on, but this tiny device, which falls in the small density FPGA, can implement multiple of these devices. So Lattice focuses on small FPGA and mid-range FPGA. So what we define as small FPGAs is any FPGA that is up to 100,000 logic cells or 100,000 lookup tables. We're going to see the details of the architecture later on. And these FPGAs, even the small ones, will integrate embedded memory, DSPs, PLLs, and they can even integrate a system on chip, meaning microcontroller with all the peripherals. And we have the tools to handle all that stuff. The mid-range FPGA is the Avant family, and that goes up to 638 system logic cells. So the FPGAs are known for their flexible IOs. So all what you see in this slide, all the different interfaces that you see in this slide, whether UART, DSI, GPIO, I2S, CSI, and so on, all these interfaces could be integrated easily on almost any IO in the device. And these application actually, and there is reference design that is available on Lattice website that could aggregate all these interfaces in one single wire and send them serially between boards or between devices to minimize the number of connectors or minimize the number of traces on the PCB. So enhanced reliability and simplified testing is another advantage of FPGAs. So you have a single point of failure instead of having multiple point of failure with discrete component. Also, the board level testing versus internal testing of the FPGA. So all the logic, when consolidated inside the FPGA, could be tested with functional simulation post-synthesis simulation or RTL simulation, and timing simulation, which represent all the timing characteristic of the your design. So you're 100% sure that you meet the timing requirement or the Fmax that you need to run at. So the simulation will definitely help and have a more reliable design. You also have access to a logic analyzer that is built into the FPGA, and a tool is called Reveal from Lattice Semiconductor, with the Radian and Diamond software platform that allow you to probe internal nodes. So you could easily probe internal nodes of the FPGA and identify any potential problems or debug using this logic analyzer, built-in logic analyzer. Flexibility, upgradability, and bug fixing. Flexibility is, I mean, FPGAs are known for their flexibility and for their upgradability. So you have flexibility during the design, you have flexibility after the board is released, you have also flexibility after the board has shipped to the customer. Flexibility during design, so you can support multiple I/O voltages. You can change that during design. Let's say an external component has changed its interface, you can easily accommodate to that. You can also customize internal logic to get around certain limitations or certain bugs. Easier board layout, so you can accommodate the board layout person by offering different I/O positioning for the FPGA, since all the I/Os can perform almost the same functionality. There's also the possibility of having multiple variant of the board with the same layout but different FPGA programming. So you can program the FPGA differently to perform different function. And the nice thing also about designing with FPGA is you can have the source code for your design, for your hardware design, in a form of VHDL or Verilog. So in the case of end of life, you can retarget that source code to a different device family. The bug fixing is very useful also to update any bugs that are found after the board has been completed, the board has been released, or even at the customer side. So once the board has shipped to the customer, you can have that flexibility to fix bugs in the field with the field upgrade, and you can also even add features or functionality to the board in the field. So you can provision some logic and some extra IOs probably in the board layout and be able to do upgrades. So you have a base model of the board and you can upgrade that as you go along. So how can FPGA be lower cost? That's a good question to ask. So there's a couple of points that I'm going to highlight in this slide in terms of board testing, pick and place, and board layout that actually make the FPGA solution more attractive. Actually, for board testing, the FPGAs integrate boundary scan registers and the I/O that allow you to do testing of the whole board using this boundary scan methodology or technique, and that avoid you to have any bed of nail or any physical probing on the board, which make the testing more cost effective. The pick and place is often overlooked also. The cost of the component may be very small, but the cost of the pick and place for 100 device may add up, and that adds to the overall cost. And also the board layout. So you may have different boards that do slightly different functionality that you can probably consolidate in one PCB instead of having 3 different PCBs with a discrete component. You can have one PCB that integrate an FPGA and that allow you to save the cost of variant of the PCB. So all these factors added together will have a big potential of having a lower cost option with FPGAs, plus all the features that we've seen in the previous slide in terms of flexibility, upgradability, and all that. So now that we have a good overview of the advantages of FPGA, let's go explore the gates and logic element that will be used for building any digital logic. So logic levels and signal definition. So FPGAs has very flexible IOs. They comply with the standard of the industry. But in order to have these IOs capture the one or zero in the right way, the true or false in the right way, you have to comply with the specification and with the standard itself. So there's certain voltage criteria that need to be met in order to recognize the input as high or low. For instance, if we take the LVC MOS 3.3, which is represented here, so you have the signal to be recognized as 0, it has to be less than 0.8. To be recognized as high, then it has to be between 2 and 3.4 volt. So if you comply to this voltage limit, and this is a standard limit, then the IOs will be recognized, the input of the IOs will be recognized properly. Same thing for the output. So there is a voltage level for the output also. Know that gates are made from transistors. I'm not bringing anything new here. So what we see here is an inverter, which is the most basic element of any digital circuit, where we have two transistors back to back with one inverted and one connected directly. And the function we actually perform here is inverting the input A to be represented in the output B. So if A equal to 0, then this transistor is off and this one is on, and we have the B as 1, and that's what is represented in this truth table. If input A is 0, output B is 1. If input A is 1, then the output B is 0. So we just designed a simple inverter. In the same way, we can build an OR gate with these transistors. So if either A or B goes to 1, then this input, or C inverted, basically goes to 0, and then this transistor is disabled, this one is enabled, and you have the C as 1, which represent the OR gate implementation. And there is 2 power n combination, depends on the number of inputs, and the truth table represent these different combination of A and B. So what is combinatorial logic? So all what we've seen in the previous slides is combinatorial logic. It's OR gates, AND gates, NOR gates, and so on. It's actually a digital logic implemented by Boolean circuit, where the output depends solely in the input, and that's what we've seen in the previous circuit. So in combinatorial logic, the output of the combinatorial logic always depends on the input. So any change on the input, in this case A or B for this AND gate, will impact the output, but after a certain propagation delay. So the delay it takes for the output to be changed, or for the signal to propagate through the transistors that we have seen in previous slides. So in this case, we have A and B, we have A changing, then it takes a TPD, or propagation delay, to have the output well represented or corresponding to the A and B logic. So there are limitations for combinatorial logic. As you have seen in the previous slide, output change immediately after the input, but after certain delays. And if the inputs keep changing, or there's glitches in the input, the output is impacted. So you may have a false output that is not filtered out. And these undesired triggers make the design unpredictable or unreliable. We cannot rely on the design. The other thing is anytime the technology changes or the process node change, the device change, that propagation delay will change with these different variant of the board, which make that TPD changing from one technology to another, or one implementation to another. Especially in FPGAs, TPD depends on the number of level of logic. So you may have implementation A that has 2 level of logic, implementation B which places things a little bit differently, then you have a different propagation delay. So we need to make FPGA designs more predictable. How do we do that? So the answer is using synchronous logic. So the synchronous logic is the type of logic where the state changes are synchronized by a clock signal. The clock signals will condition the change of the output. So the main component of synchronous logic is called the flip-flop or register. And this component, the flip-flop, has a D input, a Q output, and a clock with a reset or preset. And the truth table is represented here. So we actually have the Q at time t and Q at time t plus 1. So if D input is 0, at time t the Q output is 1, then at time t plus 1 the Q will follow the D input, and that's conditioned by the clock edge, could be rising edge or falling edge. So to have this flip-flop or this register work properly, we need to comply to certain timing parameters. So these 3 main timing parameters: setup time, hold time, and clock to out. And these will guarantee that the flip-flop operates reliably. We are sure that the output is stable. We are sure that the input is captured the right way. And like you see in this diagram, we have the clock running here. So we have the rising edge. We have the D input. So the setup time is basically the minimum amount of time that input has to be stable before the rising clock edge, or before the clock edge. And the hold time is how long that signal, what's the minimum amount of time that signal need to be stable before, after the clock edge. So this will guarantee that the data is captured reliably and transferred to the output. And the time it takes for that data to be stable, or for the Q output to be stable after the clock edge, is called the TCO time, clock to out time. So it takes a certain time to stabilize the output. Before that time, the data may not be fully stable. So if we comply to these timing parameter, we'll have a reliable operation of the flip-flop. So the question then is how fast we can run this design. So since we have this clock, how fast can we run this clock to have the maximum frequency? The frequency will depend on this delay. So we have the flip-flop A, for instance, and B. So we have logic between these 2 flip-flops, and this logic, in order to have the signal propagate through this logic and get to the next flip-flop, we have to take into consideration the TCO, so the time it takes for the Q output to be stable, then the time it takes to go through this combinator logic, plus the setup time and hold time. So all these factors added together will give us some time, and that time inverted multiplied by 1,000 will give us the Fmax. So let's say X is 50 nanosecond, then our maximum frequency is 20 megahertz. If we have a smaller X, or a shorter time in the propagation between the 2 flip-flops, then we have a higher frequency. So what is synchronous logic? So synchronous logic is composed of gates and flip-flops. that are configured to change output at a regular intervals, which is the clock, which that is considered as the heartbeat of your design. The output can also change based on the, not only based on the input, but also based on the output. So the output would be fed back to the logic in order to determine the next step. That's how state machines work. That's how counters and so on are built. So that's synchronous logic. So let's take an example to consolidate all this. Let's say we have different power supplies on the board. We have a 3.3 power supply, 2.5 and 1.8. We have a power good for each one of these. And we want to generate a reset to the CPU that has to be asserted at least 20 nanosecond after all the power supplies are stable. So now we know that we need to do an AND gate. So we are doing AND gate between all the power good signals, and we invert them because we need a active low reset. And obviously these delays propagating through all these different gates. So that's the TPD basically, but we have power good at some point. So now to have a predictable 20 nanosecond, we cannot not use combinator logic. We have to build some sequential logic using flip-flops. And in this case, we use 3 flip-flops. So we have flip-flop 1, 2, and 3 with their corresponding output. And we are getting the input D going low at some point here. So the next clock edge will make Q1 going low, the following clock edge will make Q2 going low, and the third clock edge will make Q3 going low. So we know that we have at least 20 nanosecond of delay between the time that the combinator logic provide the all power good signal and the time we have this reset communicated to the CPU. So embedded memory, that's another very important component in FPGA architecture, and we're going to see more of that in the next couple of slides. So what is a memory block? So a memory could be thought of as a collection of registers. So let's say you have a 16-bit memory. So it's like we have 16 registers that are storing either 0 or 1. In order to access this memory, we can access each register separately, but that will be a lot of control or a lot of signals that we need to provide in the input to get the output. So we could be doing the addressing of all these registers. We have 4 input signals as in address lines. And these 4 inputs will allow us to address any bits in this memory block. So if we have a 000 memory, we're going to be addressing location 0. If we have 001, we address location 1, and so on till we get to location 15 of the memory. So how is this memory element helpful in FPGAs, or what is the use of memory in FPGAs? So let's take this example where we have a memory, 16-bit memory location with all zeros, but the last case, last location as 1. So if we build a truth table with all these different combinations that we have, so if we have A, B, and C as address lines as 000, we're going to get 0 as an output, and all the other options also provide a 0 as an output. The only options that provide us a 1 is when all the address lines are 1. So we are actually, if we consider these 4 address input as logic input, we just build an AND gate. We just emulated an AND gate with using the memory location. This is very important. That's how all the logic in the FPGA is built. The combinator logic is all using this principle. So based on this memory, 4 input lookup table. So we actually call that 4 input lookup tables. That's where from where the name of 4-input lookup table come in, it's actually a memory, a 16-bit memory that will be used to build the logic. So with this 4-input lookup table, we can build any logic, any combinator logic. We associate that with a flip-flop, and we have a bypass option if we want to only build combinator logic and go to the next stage, build a bigger combinator logic. And a clock, we just define the basic building block of an FPGA. That's the called the logic cell, actually. So let's take an example of real architecture for the Nexus family. So in this case, the Certus Pro NX architecture is listed or is shown in this slide. And this is the logic cell or the basic building block of an FPGA. If we associate these shared logic or shared resources between two logic cells, neighbor logic cells, that's called a slice. And four slices will build a PFU. Actually, a PFU will have 8 logic cells or 4 slices. They are named for reference A, B, C, and D, and this is useful when you use the software. You'll be able to identify how logic is implemented within the design. So there's thousands of these PFUs in the fabric associated with EBRs, DSPs, IO banks, and other hardware functions like ADC, OSC, SPI, I2C, and some security features built in, and high-speed SerDes. That's the architecture of Certus Pro NX FPGA. So Nexus is actually a platform for multiple devices offered in the Nexus platform, and they use a 28 nanometer FD-SOI technology. There's multiple variants. So Crosslink NX is targeted to embedded vision. It has hardware features that are well suited for embedded vision processing. With MIPI type of interface and USB 3 interfaces and so on. Certus NX is general purpose processing that has PCIe and gigabit Ethernet built in. Mac NX is targeted to hardware security, so for any cyber resilient system control, the PFR implementation or root of trust implementation could be used in the Mac NX. Certus Pro NX is a general purpose FPGA that has high-speed SerDes, LPDDR, memory interface, and PCI Express and so on, so other features. And Mac XO5 is targeted to advanced security and control applications. So the competitive positioning or the competitive benchmark for Nexus family compared to competition in the same space shows that Nexus offer up to 4 times lower power than the competition. It also offer much smaller packages, up to 6.5 times smaller package than the competition. So now that we know what is an FPGA, the architecture of the FPGA, and the advantages of FPGAs, let's go through some design techniques. So what is the difference between throughput and latency? When you making decisions about the architecture of your FPGA implementation, you have trade-offs to decide on. And some of these trade-offs will be throughput versus latency. And we're going to see some examples in the next couple of slides. But throughput is defined as the amount of data processed per clock cycle, expressed usually in bits per second. Whereas latency is the time it takes for the input data to propagate and be ready at the output, and usually expressed in units of time or a number of clock cycles to get the output ready. So how can we have a higher throughput design? So there's a couple of techniques that could be used to increase the throughput of the design or the Fmax associated with the design. And these techniques will depend on the resources available, on your objective, on the architecture that you have. So, and we're going to go through a couple of examples of implementing a design different ways, using pipelining, using parallel structure, or using a loop or unrolling the loop. And each one of these implementation will have some advantages and disadvantages. And that's what we're going to see in the next couple of slides. So let's start with the register pipelining. So we have the design on the left-hand side where we have A, B, C, and D, and we want to multiply all of these input together. So a possible implementation is to use a cascaded multiplier. So we multiply A and B, then we multiply the output with C, then the output of M2 will be multiplied by the value of D, which will provide us with the final output of the cascaded multipliers. So in this case, we are using five register